that we need to model, and this is just a simple one actually, but there is a trick to it. There is something important in here. Let's see what that is. A baker has 30 ounces of flour and 5 packages of yeast. Baking a loaf of bread requires 5 ounces of flour and one package of yeast. Okay. Each loaf of bread can be sold for 30 cents. The baker may purchase additional flour for 4 cents per ounce or sell leftover flour at the same price. We can buy or sell, formulate and solve an LP to help the baker maximize profits, which is revenue minus cost. Now, this is just a question from the book, which you might be familiar with, and it says that we will define x1 as the number of loaves of bread baked. So this is where our income will come from. At least one part of it will come from. And x2 as the number of ounces by which flour supply is increased by cash transactions. Now, this might be an increase or it might be a decrease as well, because we can, sell it as well. Okay, we can buy flour or sell it as well. So x2 can actually be greater than or less than 0. So we can either buy and increase our flour supply or sell and decrease it if you want to. And as you can see, it's written here as well. Now, with this, we can just model this question in the form of, x1 and x2, in terms of x1 and x2. And for that one, we have to find out how much of which, raw material we are using to produce just one loaf of bread. So it's 5 ounces of flour and one package of yeast. And I have 30 ounces of flour. So I actually have to use 5x1 because x1 is the number of, loaves of bread I'm gonna bake. So 5x1 for everything. So 5x1 is going to be less than or equal to 30 because I have 30 ounces of flour, okay? But I also know that I can buy more flour with x2. So what I will actually have is, let's just annotate it over here, text. What I actually have is 5x1 is less than or equal to 30, okay, I'll try 30 plus x2. Why? Because I'm buying more flour, but I might also be selling that flour. So x2 can be a negative value as well. It's okay both ways. But this is my flour constraint, okay? This is the flour. So, flour, what do I also have the yeast constraint, which is 5 packages of yeast. Okay, so it requires 1 package of yeast, which means that x1 is less than or equal to 5. And this is the yeast constraint. So this one is the yeast constraint. Now I have my 2 constraints. I have also sign restrictions, etc., but I don't need them right now. I also know that I need to maximize my profit. So how to maximize it? So I have to write my profit first. I can sell each bread at 30 cents. So 30x1 is a profit. I can also sell any flour I have. If I buy it, okay, then that's a cost. So if x2 is greater than 0, this is the cost. So it should be minus x2, but the cost is 4, so minus 4x2. Now, as you can see, x2 is the number of ounces I'm buying, okay, for the flour. So the more I buy, the more of a cost I incur. I could also write, if the prices were different, I had to do something else, but as the buying and selling is the same, I can just write 4 here. If x2 is negative, then I'm, selling that excess flour and I'm getting more money for it. So if x2 is negative, then this term, this part becomes a positive because minus times minus is a positive. So I'm getting a positive value. I'm getting an income from here as well. But if it's positive, x2 is positive, then I'm getting, I'm incurring a cost over here because I'm buying more flour. But if x2 is positive, I'm increasing my flour constraint. If x2 is negative, I'm decreasing it because I'm selling it, okay? The answer is obvious. X1 is equal to 5, so because it can be 5 at most, so I will have x2 as minus 5, so I will sell 5 more, etc. But to be able to solve it using simplex, I have to get rid of this x2 because this is a URS. X1 is greater than or equal to 0, but x2 is URS. So this isn't solvable by simplex yet. I need to get rid of this URS version. So what I need to do is just turn this x2 into a new, variable, into two new variables actually, and I can just write x2 is equal to x2 like this. I have to, yes. Now, when I write it like this, when I write x2 as, this in this form, I get two variables instead of that one variable. And from these two variables, one of them will be greater than 0 and the other one will be 0 all the time. So let's just see if we did it right, and we will just, clear these and go down, and we will see. Now, yes, this is the same thing as you can see. We have minus 4x2, we have plus x2 over here, the flour constant, the yeast constant, they're all the same. But as I said, this x2 has to be changed into this form. So I write this form, this term, instead of x2, wherever x2 is. And I get this model. Now, from here, I can see that I have three decision variables, x1, x2 dash, and x2 double dash. Now, from here, I have to turn this into the standard form to be able to solve it with simplex, because it's asking us to solve it with simplex, okay? Formula can solve an LP. So all I have to do is just turn this into the standard form. Okay, I have two less than or equal signs, so two constraints that I need to add select values, plus s1 plus s2, and I can send these x2 dash and x2 double dash to the left hand side as well. So there's only the scalar unit, scalar value left on the right hand side, because that's the way simplex works. So what we get is, from this, when we solve these questions, let's see, minus 30 for minus x4. Okay, what is it for and minus x4? Let's take a look. This form, we need to change this into standard form. So we will send 30x1 to the left hand side, minus 4x2 dash to the left hand side, and plus 4x2 double dash to the left hand side. So minus 30 plus 4 minus 4. Let's take a look. Minus 30 plus 4 minus 4. Okay, right hand side is 0. This is the left hand side. So the objective function is in the standard form now. I have to do the same thing for the constant as well, sending these two to the left hand side and adding an s1. So it's going to be 5 minus 1 plus 1 plus 1, I guess. 5 minus 1 plus 1 plus 1, and I will have 0 for s2, because s2 is for the second constraint. So we are just adding s2 over here, 1 1 5. So 1 1 5. Now this is our initial table, the starting table, the basic feasible solution. From here I need to find the most negative, because it's a maximization problem. I need to find the most negative value in the objective function, which is minus 30. So I will get the ratios for 5 and 1. 30 over 5 is 6, 5 over 1 is 5. So this is my pivot point. This is already 1, so I don't need to change this, row anyway. This can stay as 1, but I will just multiply this with 30 and add it over here, and I will multiply this with minus 5 and add it over here. So every value in here will change. Let's take a look. Times 30 becomes 0. Times 30 stays the same, stays the same, stays the same. This one becomes 30, and this one becomes 150, because 5 times 30 is 150. So this will be 150. Same over here, 150. For here, I'm looking to multiply this with minus 5 and add it over here. This one will become 0, minus 1, 1, this will stay the same. This one will become minus 5, and this will become 5, just 5. So I will have this table. Now I have minus 4. This is the most negative value over here. So I will enter this decision variable into the solution. So to do that, I have to make the ratio test again, but there's a 0 here. There's no ratio. So this 1 will be the only feasible pivot point, and this is my pivot point. All right. So what I have to do is just turn this into 1, which is already 1, and turn everything up and down into 0. So this is already 0. All I have to do is just turn this value, minus 4, into 0. To do that, all I have to do is just multiply this row by 4 and add it up over here to the objective function. So when I multiply this by 4, this one will stay, this 0 will stay. This one, okay, this one becomes a 0 as well. This one will become a 0 as well. This one will become a 4. This is going to be 5, and this is going to be 175. So I have 0, 0, 0, 4, 10, 170. Now, as I can see, there are no, there isn't any negative value in the objective function. So this should be optimal. This should be the optimal solution. I'm checking the right-hand side. They're all positive. So there are no, infeasibilities over here. So this is the objective function, this is the best value the objective function can take, so it's the optimal solution. But there's a but over here. Can you see anything irregular over here in this table? There is something, just a little thing, irregular over here. Not really irregular, but still. Can you see it? Can you notice it? The table is correct. There is nothing wrong with it, but there's something, interesting, let's call. Now, normally, your objective functions should have 0 values for your basic variables only. So x1 is a basic variable and it takes the value 5. x2 double dash is a basic variable and it takes the value 5. But x2 dash is also a basic variable over here. Not a basic variable, but it can become a basic variable. It says that there can be an alternative solution over here because it has a value of 0. It's a non-basic variable with a value of 0 in the objective function. So this says that it can be an alternative solution. All right, let's check it if it can be. What this means is if there's an alternative solution, then that variable should be able to enter to your, enter your solution. So any one of the other basic variables should be able to exit. But when you try to take x2 and enter it into solution, you have to do the ratio test. So 5 over minus 1, no ratio. 5 over 0, no ratio. So I can't do the ratio test for this one. So this one cannot actually enter the solution. So there is no alternative solution. This is my one and only solution. Okay. And I also know that this cannot be a solution as well because I have already found what the solution would be, by mind. So I don't need x2 dash because I'm not gonna buy more flour. If x2 dash was in the solution, it would mean that I have to buy more flour, but I cannot buy more flour. It's not logical because I'm already using the max I can in the given terms. So I cannot buy more anyway. So this cannot enter, but it says that it can, but still it cannot. So this is just irregular. It's not, it's not a world-breaking thing. It's just irregular. It wants to enter, but it cannot enter because it's not in the solution anyways. Okay, so this is the final solution. So as you can see, with URS, we have to take the URS basic variable, URS variable, and turn this into 2 variables. And one of them might, or maybe none of them will enter, but still one of them might enter the solution, and we will see how it goes in the table anyway. But at most one of them can enter the solution. Okay, both of them cannot be in the solution. Why? Because when you are solving a question, for every constraint, you only get one basic variable. So at the start, in this question, you can only have 2 basic variables. And when you turn this into this form, you still can have only 2 basic variables. So in here, the basic variables that are going to take the value, we already know that are x1 and x2. So it should be x1 and one of those x2 dash variables. It cannot be both of them. You cannot have 3 basic variables. That's why one of them has to be 0 and the other one can take any value. Okay, both of them can be 0 at sometimes. Yeah, the model can come up like that, but they cannot both be positive. Okay, this is that's happening here. It says that, okay, I can be positive as well, but no, you cannot. Okay, so this is 5, right? x2 double dash is 5. So I could be 5 and it can be 10. That's allowable. No, it's not. Okay, it can't happen. It thinks that it can happen. Okay, as you can see, I have an alternative solution. No, you don't. You cannot be ratio because there can't be more than 2 decision variables, 2 basic variables, sorry, in this model. Okay, this is what's happening over here.